A machine the length of 1.5 football fields just finished chewing an 11-kilometer hole through solid riverbed, 89 meters beneath the surface of the Yangtze River, under water pressure 10 times greater than what you feel standing on dry land. And it did it with an alignment error of just 12 millimeters over the entire distance. That's not a rounding error in an engineering report. That's the difference between a tunnel that lets a bullet train scream through at 217 miles an hour without so much as a wobble, and a catastrophic failure buried under one of the widest, most unforgiving rivers on Earth. On March 29th, at 3:07 in the afternoon, Beijing time, engineers watched a giant cutter head break through to daylight on the far bank of the Yangtze, marking the completion of the underwater section of what is now the longest and largest cross-river tunnel ever built for high-speed rail. The machine responsible for this is called Linghang, and understanding what it just did requires understanding exactly how absurd the challenge in front of it actually was. Picture the scale first, because numbers alone don't quite land until you compare them to something familiar. Linghang measures 148 meters in length and weighs approximately 4,000 tons. Its cutter head spans up to 15.4 meters in diameter, roughly the height of a 5-story building, rotating continuously as it grinds forward through clay, sand, and stubborn pockets of residual basalt left over from the geological history of the Yangtze estuary. This isn't a drill in any sense a home renovator would recognize. It's closer to an entire underground factory moving forward one careful bite at a time, chewing through the equivalent of a 5-story building's worth of riverbed with every rotation. To really grasp why a machine this size was necessary in the first place, it helps to understand what shield tunneling actually involves as a construction method, because it's fundamentally different from blasting or conventional excavation. A shield tunneling machine works by advancing its enormous rotating cutter head into the ground, while simultaneously supporting the freshly excavated cavity behind it with a protective steel shield, preventing the surrounding soil and water from collapsing inward before permanent tunnel lining segments can be installed. Behind the cutter head, the machine essentially functions as a mobile factory, extracting excavated material, transporting it back out of the tunnel, and installing massive precast concrete rings to form the tunnel's permanent structural lining, all while continuing to push forward. Every stage of that process has to happen in tightly coordinated sequence, because pausing or slowing at the wrong moment, particularly in unstable, waterlogged ground like the Yangtze riverbed, can allow pressure imbalances to develop that threaten the stability of the entire excavation. The machine advanced along a single-drive excavation distance of roughly 11.3 kilometers, a new global record for continuous excavation using a shield tunneling machine in this size class, the 15-meter category, which represents the largest diameter classification the American Society of Mechanical Engineers recognizes for railway tunnels anywhere in the world. Over the course of 23 months, Linghang advanced at an average pace of about 16.8 meters per day, grinding forward beneath one of the busiest, most economically significant waterways in Asia, all while maintaining an alignment precision of just 12 millimeters across the entire 11-kilometer stretch. To put that number in perspective, that's roughly the width of your thumb, held as the acceptable margin of error across a distance longer than most international airport runways, stacked end to end. Now let's talk about the depth, because 89 meters is the number that anchors this entire story, and it deserves to be unpacked properly, rather than just repeated as a headline statistic. 89 meters below the surface of the Yangtze puts this tunnel roughly as deep as a 30-story building is tall, except instead of building upward into open air, engineers had to push that same distance downward through unstable, waterlogged riverbed sediment, with the full weight of the Yangtze River pressing down from above. At that depth, water pressure reaches somewhere around 9.5 bars, close to 10 times normal atmospheric pressure at sea level. That's the kind of pressure environment that, without extraordinarily precise engineering, would crush equipment, destabilize surrounding soil, and threaten catastrophic collapse before a single meter of usable tunnel could be completed. One description of the challenge, offered by engineers involved in the project, captured it about as vividly as possible. Excavating beneath the riverbed at this depth is like drilling through tofu, except the drill in question is the size of a 5-story building, and there's roughly 10 times normal atmospheric pressure bearing down on top of it the entire time. Soft, wet, unstable material that offers almost no structural integrity of its own, combined with crushing water pressure and a machine large enough to level a small apartment block. That's the environment Linghang had to operate inside continuously for nearly 2 years, without a single catastrophic failure along the way. So how does a machine actually survive, let alone perform precision work under those conditions? The engineering answer involves several layers of technology working in concert. And it's genuinely worth walking through, because this is where the story stops being about brute mechanical force and becomes something closer to precision robotics operating at industrial scale. Linghang is equipped with what engineers describe as an intelligent excavation system, paired with a high water pressure sealing system specifically designed to manage the extreme differential pressure between the excavated tunnel interior and the crushing weight of river water and sediment pressing in from every direction outside the shield. Crucially, the machine had to maintain what engineers call differential pressure control across its own structure, essentially managing two different pressure environments simultaneously on opposite sides of the machine, preventing the surrounding wet soil at the Yangtze estuary from collapsing inward while the cutter head continued advancing. Getting that balance wrong, even briefly, risks a sudden inrush of water and sediment that could bury the machine, endanger the crew, and potentially undermine the structural integrity of the riverbed above. Getting it right, continuously for 23 straight months across 11 kilometers of shifting geological conditions, is precisely the kind of engineering achievement that rarely makes headlines because it's defined by the absence of disaster rather than by any single dramatic moment. The cutter head itself carries 480 hardened steel discs, engineered specifically to fragment clay, sand, and the harder basalt blocks scattered throughout the riverbed without losing cutting efficiency or requiring constant replacement mid-excavation. Every one of those discs is doing continuous, grinding work against material that varies unpredictably in hardness and composition as the machine advances, which is part of why the project required such an elaborate sensing and monitoring system layered on top of the raw cutting hardware. That sensing system is arguably the most quietly impressive part of the entire operation. Engineers deployed what's been described as an integrated intelligent control platform, built around a full-process digital twin of the excavation happening in real time, alongside continuous early warning monitoring designed to catch any sign of instability before it becomes a genuine problem. Wang Yi, the project's deputy equipment manager, described the system in terms that make clear just how far shield tunneling technology has evolved beyond simple mechanical boring. The machine, in his words, incorporates an advanced tunneling system enabling largely autonomous operation through intelligent analysis and decision-making, drawing on hundreds of historical data sets and machine learning models to support efficient supervision by human operators alongside unmanned operation for extended stretches of the process. In practice, that means Linghang isn't simply a giant mechanical drill being manually steered forward by an operator watching gauges. It's a machine continuously ingesting sensor data about soil composition, water pressure, structural stress, and alignment accuracy, cross-referencing that live data against historical patterns from previous tunneling projects, and making micro-adjustments to its own operation largely on its own, with human engineers supervising rather than manually controlling every single decision. Precision sensors embedded throughout the system recorded every inch of soil movement as the machine advanced, allowing engineers to adapt almost instantly to shifting geological conditions and head off potential collapses or water leaks before they could develop into genuine emergencies. Behind that automation sat a large team of engineers and technicians working in shifts around the clock for nearly 2 full years, monitoring the excavation from control rooms positioned both underground near the machine itself and from surface command centers, overseeing the broader project. Even with sophisticated automation handling much of the routine decision-making, an undertaking of this scale and risk profile still required constant human judgment, layered on top of the machine's own intelligence, particularly whenever sensor readings flagged conditions that fell outside previously modeled parameters. Engineers described operating in an environment where the margin for error, given the crushing water pressure and unstable sediment surrounding the machine at all times, left essentially no room for complacency across the full duration of the project. A single, serious miscalculation at 89 meters below one of Asia's most powerful rivers could have threatened not just the project's timeline and budget, but the safety of everyone working inside the tunnel at the time. Lee, one of the project's senior engineers, emphasized that the team treated environmental and safety protocols as inseparable from the engineering challenge itself, rather than as a separate compliance checklist bolted onto the project afterward. Given that the tunnel's route runs beneath residential neighborhoods, river embankments protecting local communities, and sensitive aquatic habitats simultaneously, every technical decision made about excavation speed, pressure management, and monitoring frequency also had to be weighed against the potential consequences for the people and ecosystems living directly above the machine's path, adding yet another layer of complexity to an already extraordinarily demanding engineering task. Achieving that at 217 miles an hour is a genuinely different engineering problem than simply building a stable tunnel capable of handling trains at more moderate speeds. At that velocity, even small shifts in structural alignment, minor settlement in the surrounding riverbed, or subtle vibration irregularities can meaningfully affect both passenger safety and ride comfort. Every one of those variables becomes significantly harder to control in a waterlogged underground environment where pressure differentials and soil settlement never fully stop shifting, even long after initial construction wraps up. That's Precisely why the 12mm alignment tolerance mentioned earlier isn't just an impressive statistic for an engineering report. It's the specific precision threshold that makes uninterrupted high-speed travel through the tunnel physically viable in the first place, rather than an appealing but unrealistic marketing promise attached to the project. There's a longer-term engineering consideration buried inside that precision requirement too, one that extends well beyond the moment the tunnel first opens to passenger traffic. Tunnels of this scale, running beneath a major river for decades, have to be engineered not just for the conditions present at the moment of construction, but for how those conditions will evolve over the entire operational lifespan of the structure, accounting for gradual sediment shifts, seasonal changes in river flow and water pressure, long-term structural settlement, and the cumulative mechanical stress of thousands of high-speed trains passing through at maximum velocity year after year for generations. Engineers building at this depth and scale essentially have to predict and design against decades of gradual geological change before a single passenger ever boards the first train, which is part of why the digital twin monitoring system built into the excavation process matters so much beyond just the construction phase itself. That same sensor infrastructure and predictive modeling capability is expected to continue monitoring the tunnel's structural health well after trains begin running through it, providing an ongoing early warning system against the kind of slow, cumulative shifts that wouldn't be visible to the naked eye but could matter enormously over a multi-decade operational lifespan. It's also worth stepping back to appreciate what this project represents for China's domestic engineering and manufacturing capability specifically, beyond the immediate transportation benefits. Linghang was developed by China Railway Construction Heavy Industry, a domestic manufacturer, meaning the entire machine, from its 4,000-ton mechanical structure down to its intelligent sensing and control systems, was designed and built inside China rather than imported from established international tunneling equipment manufacturers in Germany, Japan, or elsewhere. That domestic engineering capability didn't emerge overnight. China has spent roughly 2 decades systematically building up its shield tunneling machine industry, moving from a position of importing nearly all its heavy tunneling equipment from foreign manufacturers to now producing some of the largest, most technically sophisticated machines of this kind anywhere in the world. Chinese-built tunneling machines in this general category have also increasingly become an export product in their own right, with Chinese manufacturers supplying large-diameter shield machines to infrastructure projects in other countries, a reversal of the technology dependency that defined this specific engineering sector for much of the previous few decades. It's worth comparing this achievement to what came before it, because the pace of progress in this specific engineering niche has been genuinely dramatic. Underwater tunneling beneath major rivers has challenged engineers for well over a century, going back to some of the earliest tunnel boring projects beneath rivers like the Thames in London during the 19th century, where progress was measured in mere meters per week, and worker fatalities from tunnel collapses and pressure-related injuries were tragically common. Even as recently as a few decades ago, tunneling beneath a river as wide, deep, and geologically complex as the Yangtze at this particular crossing point would have been considered close to unfeasible using the technology available at the time, or would have required a construction timeline stretching many years longer than the 23 months Linghang needed to complete its underwater section. The compression of that timeline, combined with the dramatic increase in scale and precision, illustrates just how far shield tunneling technology has advanced within a remarkably short span, driven in large part by the sheer volume of megaprojects China has undertaken across its rail, subway, and highway networks over the past 2 decades, each one contributing lessons and refinements that fed directly into machines like Linghang. There's a broader pattern worth recognizing here, too, one that extends well beyond this single river crossing. China has been on an extended run of setting records in exactly this category of megaproject engineering: deepwater bridges, ultra-long tunnels, high-speed rail lines pushing into increasingly difficult terrain across mountains, deserts, and now major river systems. Some of the country's other recent infrastructure milestones include the world's highest bridge spanning a canyon in the mountainous southwest and some of the longest sea-crossing bridge tunnel systems anywhere on the planet, connecting major coastal cities across open water that would have been considered prohibitively difficult to bridge just a generation ago. The Chongming-Taikang Tunnel adds several new entries to that growing list of records simultaneously. The longest single-drive excavation distance ever completed for a high-speed rail tunnel, the largest diameter shield machine ever used in this specific tunnel category, and now the deepest point ever excavated beneath the Yangtze River specifically. Setting one of those records would already represent a significant engineering achievement for most infrastructure programs around the world. Setting all 3 simultaneously on a single project, completed within a 23-month excavation window, says something meaningful about the current trajectory and ambition level driving China's infrastructure sector as a whole. None of this is happening purely for the sake of setting records, of course, however impressive the individual statistics are on their own. The Yangtze River Delta region that this tunnel serves is one of the most densely populated and economically productive areas anywhere on the planet, generating a substantial share of China's overall gross domestic product from a relatively compact geographic footprint. Reducing travel friction between Shanghai and the surrounding Jiangsu province communities on the other side of the river carries direct, tangible economic value. Faster commutes, more efficient movement of business travelers, tighter integration between manufacturing hubs, financial centers, and the workforce that keeps that entire regional economy functioning. Think about what this actually means for someone living in that region once the full line opens. A trip that currently might require navigating ferry crossings, congested bridge traffic, or a lengthy detour around the river entirely could shrink down to a matter of minutes spent gliding beneath the Yangtze at full highway plus speed, seated comfortably in a train carriage, likely without any perceptible sense that 89 meters of water and sediment are pressing down overhead. That kind of transformation in daily travel time doesn't just benefit long-distance business travelers either. It reshapes where people are willing to live relative to where they work, where companies choose to locate offices and factories, and how tightly integrated an already crowded economic region can become once a major geographic barrier stops functioning as a meaningful obstacle to daily movement. The financial scale behind this ambition matches the engineering scale. The broader project carries an estimated investment of roughly 530 billion yuan, somewhere in the neighborhood of 74 billion US dollars, reflecting just how significant a national priority this specific corridor represents within China's ongoing infrastructure expansion. And this tunnel isn't an isolated, standalone achievement either. It's explicitly framed as part of a much larger strategic plan to extend China's high-speed rail network to a total of 60,000 kilometers by the year 2030. For context on just how enormous that figure already is, China's existing high-speed rail network is already the largest on the planet by a wide margin, carrying billions of passenger trips annually and connecting cities across a landmass roughly the size of the entire United States. This expansion plan would push that lead even further ahead of every other country's rail infrastructure combined, cementing high-speed rail as one of the defining features of how people and goods move across the country for decades to come. There's also a genuinely interesting environmental angle buried inside this story that's easy to overlook amid all the engineering superlatives. Choosing to route high-speed rail underground beneath a major river rather than constructing an above-ground bridge crossing carries meaningful implications for the surrounding landscape and ecosystem. Bridges, however elegantly engineered, inevitably introduce a permanent physical structure disrupting river traffic patterns, altering wind and water flow dynamics, and creating a lasting visual and physical presence across the water's surface. A tunnel, by contrast, leaves the river's surface and surrounding embankments almost entirely undisturbed once construction wraps up, preserving existing shipping lanes, protected aquatic habitats, and the natural character of the waterway itself. Given that the tunnel's route deliberately threads through protected aquatic zones and ship anchorage areas specifically to minimize ecological disruption, that underground approach appears to have been a deliberate design choice, not merely a technical necessity dictated by geography. What ultimately makes this achievement worth pausing on isn't just the raw scale of numbers. The 89 meters of depth, the 11 kilometers of continuous excavation, the 4,000 tons of steel grinding forward beneath 10 times normal atmospheric pressure. It's the underlying combination of factors that had to align perfectly, continuously, for nearly 2 full years, without a single catastrophic failure derailing the entire project. Precision engineering capable of maintaining 12mm alignment tolerance across 11 kilometers, intelligent sensing and machine learning systems sophisticated enough to predict and adapt to unstable geological conditions in real time. Domestic manufacturing capability, advanced enough to design and build the largest machine of its kind anywhere in the world, entirely in-house, and a broader strategic vision willing to commit $74 billion and multiple years of sustained engineering effort toward a single river crossing, specifically so that a bullet train carrying ordinary commuters could pass underneath one of Asia's mightiest rivers at 217 miles per hour without so much as a shudder. It's worth remembering, too, that the completion of this underwater section marks a milestone, not a finish line. The broader Chongming-Taikang Tunnel still requires additional construction work before it's fully ready to carry passenger trains, including interior systems installation, track laying, signaling infrastructure, and the extensive testing and safety certification process that any high-speed rail line must pass through before regulators clear it for public use. The excavation breakthrough on March 29th represents the single hardest, most technically uncertain phase of the entire undertaking, reaching successful completion. But the path from a completed bore to a fully operational high-speed rail line still involves months, likely stretching into a year or more, of additional engineering work before the first paying passengers ever step aboard a train bound beneath the Yangtze. That's the story, sitting quietly beneath the surface of the Yangtze right now. Completed, tested, and waiting for the first high-speed trains to prove at full velocity that 89 meters of water, sediment, and pressure really can be made to disappear beneath the wheels of a train moving faster than most people will ever travel in their entire lives.